Hello, welcome to the part 2 of week 9. So today we are going to discuss the binary heap, right? So binary heap, in the previous session that we discussed, that it is a base data structure for a priority queue, right? And this base data structure will look like the tree structure, and not just simple tree structure, balanced tree structures. All right. So today we are going to discuss how we can create a binary heap as a balanced tree structure to implement a priority queue, right? So the binary heap for priority queue. So priority queue implementation, it works like this. First way to implement priority queue is the linked list-based implementations that we already discussed in the first part of this week. Sorted implementation utilizes the expand the in queue operations, right? And the unsorted implementations expand the DQ operations. And in queue operations, the linked lists are all sorted based upon the priority, so it's being called sorted implementations. And DQ operation, when we talk about the unsorted implementations, the DQ operations select the highest priority when it gets out the elements. So it means that the linked list itself is not sorted when it was stored, right? So it's being called unsorted implementations. And this part is going to discuss the tree-based implementations, which is going to be called in specific binary heap, right? So binary heap is has two properties. The first property is the shape property. The reason why we are using the tree-based implementation is basically make the data structure more efficient in terms of the big O notation, right? So to justify this using the tree structures, it must be balanced. It must be balanced. And in the previous lecture, we already talked about the balanced tree and complete tree, right? And balanced tree can be complete tree. Actually, it can't, not always. So complete tree is always a balanced tree, and balanced tree is not always complete tree. Complete tree always the full tree. Complete tree can be full tree, but not always. But full tree is always complete tree. For example, in terms of balanced tree, let's imagine we have a upper triangle, which is a full tree, and at the leaf level, we have a one single element dangled at some point of this children of the upper level. In this case, it's not complete tree. On the other hand, complete tree always fill in from the left to the right. So that's the definition of the complete tree, right? And yeah, it works like this. And then the full tree is always filled in. So a full tree has more specific shape, and the complete tree has more constraint in the shape, less constraint in terms of the shape, but it has more constraint than the balanced tree shape. So if we able to, let's erase a little bit. Oh, sorry. So if we are able to create a complete tree, then the mission accomplished, right? So it's balanced tree. It's already balanced tree if it is a complete tree. So we want it to be a complete tree, right? And the next thing is that the heap property. The heap property is more like a value type of property. Each node should be greater than or equal to each of its children, right? So it works like the binary search tree. In binary search tree, we have this constraint. Left-hand side is smaller than the current value. And it must be smaller than the right-hand side. We had this constraint in the binary search tree. Here, in the heap property is that in heap, parent should be bigger than this parent's children. Only that. There is no distinction of the left-hand side and right-hand side at this moment, right? So max heap, we are going to define the binary heap, but we can define the binary max heap or binary min heap. In this context, we are only going to focus on the binary max heap because that this is the heap property of the binary max heap, and the binary min heap property is actually the opposite, right? So this is binary max heap, and this is binary min heap, right? So it's so trivial, so we are only going to focus on the binary max heap. Right, so let's erase a little bit. Right. Okay, so is this a max heap? Anyone can tell me? As a starter, it violates the shape property because it's not a complete tree. It has nice upper triangle, but we have an empty space here in the middle. Means that this is not complete tree. It's not. So it's already not a binary here, right? No. And how about this? How about this? How about this? Is this a max heap? So here we have this empty thing, so it's not a complete tree as well. Furthermore, the heap property itself is that the parent should be bigger than its children. 2 is smaller than 3, so this is alright, okay, but it works in the opposite way. So this is the violation of the heap property. So it's not good. So it's not going to be a max heap, binary max heap, right? So it's no. And how about this? Is this a max heap? Actually, yes, it is. Let's find out why it is that. So it has nice upper triangle shape, and it's been filled in from the left to the right. And 7 is greater than 4 and 5, and 4 is greater than 0 and 2, 5 is greater than 3. Means that this also satisfies the heap property. So this is alright shape-wise, is complete tree. Alright, heap, the always parent is greater than children, right? So this is perfectly alright max heap, alright?